Welcome to the 27th class meeting of the Introduction to DSP. As I just told you in Korean, we are very behind the schedule. Anyway, this is the last week, and again, there will be homework. About the voluntary project, please volunteer to do that. Today, we are going to finish chapter 10, entitled Fourier Analysis of Signals Using DFT, which is the heart of this course. So last time, let me review. So last time we started chapter 10, and the key block diagram of chapter 10 is this one. So we assume there is a continuous time signal, and our objective is actually to analyze the frequency spectrum characteristic of this continuous time signal. The problem is that sometimes the continuous time signal may not be strictly band limited or even not approximately band limited. In that case, our approach using here based on the uniform sampler and DFT does not work. So sometimes just as a trade-off, we put anti-aliasing filter, AAF, to cut out any frequency content that may cause frequency domain aliasing. Then here, we perform CT to DT transformation, especially by using the uniform sampling. So T or TS, whose inverse is Fs. And here comes a discrete time signal, which is the uniformly sampled version of this one, which is already low-pass filtered. And here, if we perform discrete time Fourier transform, we would have a periodic signal with period 2 pi. Unfortunately, in this computerized era, we don't want to compute this function that is a function from R into C. Of course, W can be limited to 0 to 2 pi, but still, this set is an uncountably infinite set. So what we can do is to consider some special omega sub case, which is a fraction of 2 pi with common denominator capital N, and K ranges from 0 to capital N minus 1. And we hope from this evaluation of DTFT of X signal, we could estimate or we could extract some information about the continuous time signal. So this is the big picture. And please remember the names of each function. So here W is the window function. And now, let me draw some frequency functions. So here comes the STFT of the signal. Usually, communication engineers love using F in Hertz, but our textbook loves capital omega. So I would rather say this one. And here comes the filter response of the anti-aliasing filter. And here comes the CT to DT converter. And we have, XC of omega. And then we have here X of lowercase omega. Let me use x of e to the j omega. So lowercase omega means it is the radiant frequency for a discrete time signal. And then we have w of e to the j omega, again, with lowercase omega. And here goes v of e to the j omega. Like this. Now, here we have an example for each function. Oh, by the way, our textbook loves j omega. Let me put j here. So suppose this is the continuous time Fourier transform of the signal, and this is the frequency response of the AAF, and this is the output of the AAF, and this is the uniformly sampled version of this one, where we assume that this is half the, so this is 2 pi 1 over 2t. So this is half the sampling rate, half the sampling rate. And half the sampling rate corresponds to pi in the discrete time Fourier transform. Got it? So sampling rate determines which capital omega becomes pi in DTFT. Now, here comes the DTFT of the window function. These two will be circularly converged to generate DTFT of V. And if we choose n, some capital N, then what you do is that you divide this single period of 2 pi into uniformly spaced capital N intervals and evaluate by performing DFT. Got it? So as I repeatedly told you, what you need to remember is not only these shapes and how they multiply, the first thing, but is how the sampling rate affects your final results and how the window function affects your final result and how the number of points in DFT gives you the resolution of the DTFT. Got it? Sometimes, as this says, sometimes our length of the window function, so we assume that W of n is 0 for n less than 0 and greater than or equal to L. So window function has at most the duration capital L, some possibly non-zero. And if L is less than the number of points here, then we pad zeros. That is called zero padding. And what's the effect of zero padding given the same value of L? For example, let's fix this W of n as a rectangular window function of length capital L, say 100. Now you pad zeros, so you choose n, for example, 128, 126, is it 26? Yeah. And you may choose, no, what is that? 32, 64, 128. So let me give you an example. You may change the number of points this way. Then what happens? As I told you, n determines the resolution, and L with the shape determines the W of e to the j omega. So padding zeros and increasing n gives you finer and finer resolution without modifying the shape of this window. Got it? Actually, window converge with the original signal. And this figure gives you an example when there are two sinusoidal signals and you use, I remember, rectangular window. And even though rectangular window has good main lobe, anyway, it had some width. So the original signals, two sinusoidal signal, has smaller and smaller gap between their center frequencies. Then we may not notice that there are two sinusoidal signals. So we may need large enough window length, but in that case, we may need larger computational burden. That was, as I repeatedly told you, there was a problem when we had very small computing power. But these days, some 1,000-point FFT is not that burdensome. So we can increase the resolution very large, which means that we can increase the value of L also very large, which means that we may have very, very narrow main lobe width. But still, using a rectangular window may not be a good choice. By sacrificing a little bit of main lobe width, you may significantly reduce the side lobe height. Especially when you do some radar signal processing, you want to reduce the, suppress the side lobe. That can be done by a clever design of a filter, or sometimes in uniform linear array, you modify the weight in the complex gains to multiplied to each output of the antenna element. You can shape the radiation beams anyway. So this is what we've seen, and I just mentioned about this. So the difference here and there is that you have shorter window length L, so you have more blurring of the original signal. As you see, in this case, you have length 32, and in this case, you have length 64. Got it? We've seen that, yeah. And almost at the end of last class meeting, we talked about short time Fourier transform. And this is named in the textbook time-dependent Fourier transform. But I find short time Fourier transform is more popular. By definition, short time Fourier transform may be viewed as a transformation of X. So here goes the signal X, and here is the short time Fourier transformer. And then you have a function of two parameters. So this transformation converts a one parameter function to a two parameter function with some redundancy, depending on how you choose your window function. And remember, X is a two parameter function. And let me ask you, what is the domain of this function capital X? First, n can be any integer. So we have the set of all integers z. And here comes the product, set product. And what is lambda? Lambda is the discrete time frequency. So we may limit it to 0 to 2 pi. Of course, it could be any real number, but this period is repeated. And what is the possible value? A complex number at each pair of n and z. Ready? By the way, this is called the Cartesian product. So probably you remember some member S is in the set of A times B, then S is actually can be written as A comma B, where A is a member of capital A and B is a member of capital B. Right? Anyway, so here, this is a mathematical transformation. In that sense, people love to call it time-dependent Fourier transform rather than short-time Fourier transform. Short-time Fourier transform is often referred to as the sampled version of time-dependent Fourier transform, but it's not that strict. Some people just call this transform itself as short-time Fourier transform. But mathematically speaking, according to the notation or definition of our textbook, this is a mathematical transformation, and short-time Fourier transform is the evaluated version of this function at some specific grid. We will see. Anyway, so what is this one? This one, the inside of this one can be viewed as what? Your input is time advanced by parameter n and windowed by w, and DTFT with parameter lambda is performed. So windowed version of the advanced version of the input is discrete time Fourier transformed. And now let's see an example. So here comes a linear chop signal. And this linear chop signal is advanced by 320 as a function of m. And since this linear chop has from 0 to infinity, it has linearly increasing instantaneous frequency. If this signal is further time advanced by 400, then we have that part, by the way, we have ... here. So we may chop it from where? So somewhere to there, and we have this one. In the time-dependent Fourier transform, our window is fixed as a function of m. And here we assume that window function is this time domain Hamming or Hahn function or Kaiser window. Then this product of these two signals is discrete time Fourier transformed. Then what happens? This is what we have Fourier transformed the product of these two signals, and this is what we have. Then what is this one? This is the DTFT of the original chop signal. And as you will see, this signal has what? Has some frequency range that ranges from 0 to, for example, up to 0.3 here. But apparently, we have increasing instantaneous frequency. That information is totally lost in the magnitude of the DTFT. Of course, combining the information from the magnitude and phase of the DTFT, we can recover the original signal if we have properly time truncated. The problem of this is that since the function generates a complex number, and we usually love to plot the magnitude or magnitude scale, then all the information about the order of the instantaneous frequency, so low frequency comes first, high frequency comes late, is lost. So that drawback is overcome by the time-dependent Fourier transform. And here comes the more evident example. So here we have y of n, a discrete time signal that is 0 for n negative, and it has linearly increasing frequency, instantaneous frequency, and constant frequency, and then two tones we have. Now, if this is discrete time-dependent Fourier transform, then plotted, we may have some function. But one good thing for this time-dependent Fourier transform is that even if we ignore the phase information, still our magnitude scale after log base 10 is taken gives us the basically the instantaneous frequency. So here we have linearly increasing frequency and single tone and double tones. By properly modifying the window length and window shape, we may have worse resolution here. See that? We have these two tones almost overlapped, right? But good thing is that these are called so-called artifacts. As you will see here, there is some continuous frequency components here, but due to the abrupt change, we have these artifacts, which actually does not exist here. And this effect could be reduced by tapering the window. So if this is the rectangular window in time domain, we may have some tapering, even like that, to have less and less these effects of abrupt change or time limitation. By the way, this 20 log 10 base absolute value of the magnitude of the time-dependent Fourier transform is called a spectrogram. And spectrogram is a very good function that shows how the frequency changes. Just a second. Is it log? Yeah. So this is n and this is lambda. Okay. Divide by 2 pi, by the way. Okay. Now here goes the what we are going to study today. So I just talked about the short-time Fourier transform and spectrogram, and we are going to cover the rest of the chapter 10 that is related to the power spectral density estimation. And I thought about whether I cover this one or not, but decided to cover that, even though I said no random signal or random process will appear here. But anyway, even if this part does not appear in our final exam, I want to talk about it anyway. So by the way, we haven't yet finished about the short-time Fourier transform and spectrogram, so let's see more about that. So here, the time-dependent Fourier transform is, as I told you, the DTFT of the time-advanced and windowed signal. And you remember the invertibility of the DTFT under the assumption of, for example, finite energy assumption on X, or some cases of our very good fortune, then we have absolutely integrable absolute summable of function xn, and at the same time absolutely integrable DTFT. But usually, as I told you, we assume this is a finite energy signal for the Fourier transform exists. And from the Parseval-Plantrel's relation. If signal is finite energy signal, then this is also a finite energy signal, and their inverses exist. And if you compute the DTFT and inverse DTFT, the inverse is same as the original signal in the L2 sense, something like that. Okay. So basically, this is invertible. Now the question is whether time-dependent Fourier transform, which is the DTFT, is again invertible operation or not. And the answer is not always. It depends on your window function. If window function makes us to lose some information about the signal, then we are doomed. But if the window is properly chosen, then from the time-dependent Fourier transform, we can fully recover the original X. The problem is that, as I told you, DTFT, the time-dependent Fourier transform evaluated as specific grid is called short-time Fourier transform. So from short-time Fourier transform, we may not have complete or perfect reconstructability of X of n, depending on how you sample this time-dependent Fourier transform. So here comes the two idea. So first thing is that, I'd better say this. Yeah. Suppose you choose, just a second. So from 0 to 2 pi, this is lambda. Suppose you choose n points only, then let me tell you. So let's see this one again. If this is time limited, W is time limited, and if we choose to evaluate DTFT at 2 pi divided by n times some k, then this computation of DTFT replaced by DFT. So we want to use DFT. In that case, we are not evaluating every lambda here, but we are evaluating on capital N points. In that case, each output can be rewritten as the LTI filter output sampled at a specific time instant. If we sample 0, then sample at 0, 1 here, something like that. So this is the filter bank interpretation of the time-dependent Fourier transform when we choose lambda equals 2 pi times k over n. Got it? So be careful. Time-dependent Fourier transform is not necessarily evaluated by DFT or FFT. We can evaluate time-dependent Fourier transform if the window is time limited, and also we want to evaluate at some fraction of 2 pi, which is the integer multiple of 1 over n, 2 pi over n. So when we evaluate this way, then we may call it as short-time Fourier transform. Anyway, so from the short-time Fourier transform, not only the time-dependent Fourier transform, we may, in some cases, perfectly reconstruct the original signal if we do not ignore or remove the phase information. Still be careful. If we just stick to spectrogram that does not retain the phase information, we cannot recover the original signal perfectly. By the way, there are some applications of short-time Fourier transform or time-dependent Fourier transform, and that looks like this. Sometimes what we do is that we perform short-time Fourier transform and do some signal processing, and then we try to synthesize the signal by kind of inverting the two-parameter transform to get y over n. It's similar to, for example, continuous time signal, and we process it using A to D converter. We perform discrete time signal processing, and then we use digital to analog converter. That kind of thing happens again and again. And here comes the time-dependent analysis part and time-dependent synthesis part. If we can approximately or perfectly reconstruct the signal given the window function. And again here, this could be replaced by short-time Fourier transform, which samples the time-dependent Fourier transform, and this is short-time inverse Fourier transform. Then, since we are kind of time limiting this one, again, when we synthesize y over n, our old technique, the overlap add method, we've learned in the application of FFT or DFT, can be again used. And this figure shows the filter bank interpretation of the time-dependent Fourier transform. And as you see here, this is the time-dependent Fourier transform. And if we evaluate at specific lambda, then it could be shown as the convolution of x with this function, defined that way. The impulse response is the time reversed window times e to the j lambda n. So each filter, h lambda, has this impulse response. And since we have a fixed time reversed window modulated, by changing the value of lambda, we shift the spectrum of the filter in the frequency domain. And here goes an example. Okay, so we have one, probably this way, spectrum of window, and then we shift, and the entire frequency of 2 pi, so this is omega, is fully covered by, in this case, how many? 16 of them? Yeah. So is it 16? Yeah, 16 filters cover the entire 2 pi. And in this case, we have slightly different window case. And each window has shorter period, so it has more larger. I don't remember that. Yeah, this is Kaiser window case. So the upper one is rectangular window case. So each one is a Dirichlet kernel. And here, the spectrum is different. It has wider main lobe, but has very small side lobes, even though in both of the cases, each window overlaps a lot. Got it? So anyway, so there are many, as I emphasized, many applications of FFT whose original transformation is DFT, and that is related to the DTFT when the signal is time limited. So we can use FFT, a lot of different applications. And you may find yourself those applications in your research. And here comes another application. And this is, as I told you, will not appear in the final exam because I promised not to cover random process part. But I have to talk about it. So this section 10.4 and 5 are more related to random signal processing using FFT. So first thing is that when you handle random process, what is it? It is a signal with uncertainty. And uncertainty is statistically modeled. And if I talk about what is a random process, probably I have to spend entire semester to explain it. So I will not talk too much about it. But first thing is that a random process is classified as a stationary random process or a non-stationary random process. And random process has, as a special case, a deterministic signal. So we may somewhat generate a deterministic signal and call it a non-stationary signal. So here, the examples in section 10.4 looks more like a deterministic signal, but does not have so-called stationarity. The problem is that what is then stationarity? And to talk about that, I have to spend a lot of time to explain, but let me be just quick. Stationarity means that something does not change over time. So the basic idea is something does not change, even though signal has a lot of uncertainty or randomness, so-called. Something does not change. And the level of something determines different levels of stationarity. And we may have strict sense stationarity, and we may have first order stationarity, we may have second order stationarity, we may have so-called wide sense stationarity, and sometimes cyclostationarity and some other things. A lot of different levels of stationarity. But anyway, something does not change allows us to estimate or extract some information from the observation of a random process. And one of the tasks is extracting the information in the frequency domain. And frequency domain means that we perform some Fourier analysis. So here goes the Fourier analysis. This figure is already given to you when I talked about my own experience of taking the speech signal processing. And here goes the utterance of 2 plus 7 is less than 10. And what is it? It's actually the spectrogram. So we use short-time Fourier transform by properly choosing the window length and by properly choosing the FFT points. We may see this time domain signal in the time frequency domain. So this is frequency and this is time. And we have aligned intentionally. And can you see? Here we have some very fast moving component and something, but in the time domain, we cannot distinguish it properly, but you see some things here. And as the dark side means that we have more energy there, what happens? Here, the kind of high energy frequency increases here, right? And here, we have decreasing frequency. Probably this is due to when you pronounce 7, not 7. Got it? So we have some decreasing frequency instantaneous frequency there. And these informations people initially thought could be used to recognize what is uttered by a person. So long ago, not this age of LLMs, people tried to use short-time Fourier transform in speech processing. So they filter the signal, and if the output of some filter and some another filter maximizes in that sequence, and then people say, okay, this sound could be 7, something like that. Of course, that didn't work well. And I still remember when I was at your age, there was an undergraduate seminar, and one of the, was it LG Electronics or Samsung Electronics? I don't remember. But he was the developer, the engineer in the so-called 백색 가전. So at that time, the company was producing a microwave oven that recognizes the command by voice. So it's like I open the microwave and put something, and sometimes I had to rotate the dial or push button, but they want to replace that. Like 1 minute, 1분. Then the machine recognizes and just hits for 1 minute. And the engineer said that they almost perfectly made their microwave oven to work. And then they invited their probably CTO or some very high-ranked person. The problem was that he had very, very severe intonation, probably from Daegu or Pohang area. And probably he said not 1분, 1분, something like that. And due to this totally different tone, it didn't work. And he said that the engineers had a hard time, something like that. Anyway, but still, this technique is quite often used in the digital forensic. For example, when we, when we make up a person's voice or combining them, then sometimes what happens is that the background noise level suddenly increases. So by just plotting the short time at the spectrogram, you may see that sometimes this part and that part is from different environment of noise. For example, here, our air conditioner just started to operate again. And you want to chop some parts of my lecture at this moment and combine with other segment, then maybe I may say that we have no final exam, something like that. But, and you may say that, hey, professor said there is no final exam, but I examine the background noise level and say that, hey, something's wrong, blah, blah. Actually, that is what happened. Probably it is almost before you were born in one of the presidential election. So one of the candidate of a party had some suspect that his son illegally got exempt from the military service. But there was no proof. And suddenly, one of the supporters of the opposing party said that he had the evidence recorded in his voice pen. And initially, that opposing party had a press conference and played that sound, but the quality of the sound was very, very poor. Anyway, they said that they will provide that evidence to the police, but they delayed and delayed until the voting day came. Anyway, so people had no idea whether to believe this candidate's claim that his son was not illegally exempt from the military service, or the opposing parties claim that they had the evidence. And interestingly, the police later, after the election, by the way, the candidate with suspicious son lost the presidency, lost the election anyway. But later, they examined the so-called evidence and found that that was almost completely made up. So, but that does not mean that the son of the candidate was really legally got the exemption. Maybe that is still true. Because all the metrics, height, weight of that son of the candidate, almost a reasonable person couldn't believe such a person could leave and get the military service exemption. But anyway, there was no hard evidence. So probably this guy, by the way, he was imprisoned later due to the forged evidence, made up the evidence, assuming that those scientists and engineers in the police could not find out the trick he used. Anyway, so spectrogram is one of the basic tools in analyzing any speech or acoustic signal. And that can very vividly show approximately at what time instant, at which frequency you have high energy. Got it? But sometimes you had to hand tune your window size and your resolution. That is the problem. So long ago, compared to this current time, people had tools, but those tools needed a lot of exercises and experience. One good thing at this point is that sometimes just a simple voice command provides a lot of different variations of the outputs. And we are living really an artificial intelligence era. Anyway, and this short-time Fourier transform is not only used in this digital forensic of some acoustic signal, it is also used in radar signal processing to find out the Doppler frequency shift. By the way, in that case, you may have to use chop transformations we've seen already, and sometimes simple modification of almost the standard algorithms may give you a kind of breakthrough in your project or research. So whenever you have some Doppler frequency shift estimation, go back to your DSP course and read the parts in the textbook. Now, anyway, this could be the last part of this class meeting. So here comes the power spectrum estimation using FFT. And that is related to periodogram. By the way, we've seen a similar terminology called a spectrogram that is related to short-time Fourier transform. And this is called a periodogram. And here comes the idea. So what you want to do is to estimate the power spectrum of the random process for stationary random process. So the previous section was for non-stationary signal. And we've seen in the time domain some so-called formants of voice changes, right? Now, in this section, we don't have such a thing. So we don't need to use short-time Fourier transform. But we again use a DTFT or a DFT. Got it? There are two methods to estimate the spectrum of a stationary random process. One is so-called the periodogram approach, and the other one is auto-covariance sequence estimation approach. And they are both based on the definition of the random process and equivalent definition derived from Wiener-Khinchin theorem. So they are both approximation of the definition of PSD, power spectral density of a random process. The problem is that you don't know, or you may have forgot what is the power spectrum. So I have summarized definitions first. So here comes the definitions. Left block or column is for the continuous time random process. Of course, stationary, not necessarily stationary, but continuous time random process. And this is for discrete time random process case. Suppose we have x of t. And power spectral density is defined first. You time truncate the random process. Hey, that is good, right? It's similar to doing some multiplying a window function. So here in the discrete time random process case, you exactly multiply x with some window. Here, for simplicity, I assume the window is symmetrical. So this is kind of W of n. Now, what we do is that we Fourier transform this signal. By the way, forgive me about the abuse of notation. This and that function are different functions. They are not just the replacement of the variable. This is the Fourier transform, but I just, let me use. Or if you really hate, okay, let me use V here. Okay. Got it? So X is Fourier transformed to have V. And this V is a random signal again. So we take the average of the magnitude square. And we divide it by the length of the window, 2 delta. And if the limit of this function of f, by the way, this is a function of frequency. If it converges, then it is called the power spectral density of the original random process X. Similarly here, in the discrete time random process, we first window the signal. Here, we assume that the length is L, and we Fourier transform, now discrete time Fourier transform, and we take the magnitude square and take the ensemble average and divide by length L. And if this one, when L tends to infinity, converges, then it is defined as the power spectral density of the discrete time random process. So this is the definition. And periodogram approach tries to mimic this definition. Got it? And the alternative method is related to the Wiener-Khinchin theorem that gives you an equivalent definition of the Fourier transform. But anyway, let's see the periodogram approach first. So here, we have a stationary random process X. But unfortunately, we assume that we have a single observation. of X. Now we multiply a window W and define it as V. And we perform discrete time Fourier transform. That is V of e to the j omega. The problem is that we don't have any other observation. So we may not rely on ensemble average. So this average is just dropped. And also, this limit operation is dropped. So what kind of approximation is done? This is not performed. That is not performed, but just energy spectrum of the time window of the signal is divided by the length of the window. And you may say that, hey, then what is this U? And we have a long story. When we build an estimator, sometimes we have so-called bias. And this U, a constant, is to just simply scale the entire periodogram to make it an unbiased estimate. And about the details, you find it yourself. Sometimes we just put 1 here. And as we will see in the next subsection, if we do some periodogram averaging, then bias becomes small and small. So that's okay. Anyway, so as I wrote here, no averaging and no limit, but just scaling to make it unbiased. Got it? And of course, this can be generalized, or this problem may be dropped when we have multiple observations, or if we have very large observation of single realization. So suppose we have x of n observed from 0 to 1 million. And we know that this random process is stationary or approximately stationary, and this width is large enough. Then there are direct methods to use very large window lengths from 0 to 1 million and compute the periodogram just using this one only. Another one is that we divide it into many segments. Of course, we assume that if we observe this one, then we have enough length to extract our information. In that case, suppose this is the first, let me use zeros, and first, second, and capital K minus 1th segment. And what we do is that we compute the periodogram by using this smaller segment. And we find periodogram using this smaller segment. But what we do is that we average the periodograms. In that case, as far as we have stationarity, and actually ergodicity, but not only the stationarity, but also ergodicity, then we may replace this statistical average an arithmetic average. So in Korean, 통계적 평균이 산술 평균으로 대치되는 거죠. So by doing this periodogram averaging, we may have better estimate of the power spectrum. The problem is that given a single realization of very large length, if we want to increase this segment size, then we have to decrease the segment length, right? Number of segments increased means that the duration of each segment reduced. Then what happens? Our resolution in the frequency domain decreases because this is reduced. So we need a trade-off. But we may have some trial and error to find what is the good choice of this length. Probably the textbook says length is Q and K. Got it? So this is the so-called periodogram averaging technique. By the way, here I have written some complete view about the estimation of a continuous time random process, but it requires sampling, and we need some strange 1/t for the spectrum folding. So if you have to use this periodogram averaging approach to estimate the power spectral density of, for example, OFDM signal or something, then be careful about scaling. Okay? So if something's wrong and you don't know what is going on, then look up this page and study carefully, and you may find, hey, got it, what was wrong. Anyway, so here comes the Wiener-Khinchin theorem. And the Wiener-Khinchin theorem is for continuous time random process. And also we have a discrete time random process version. And this theorem is very interesting. So given a continuous time random process x of t, the power spectral density was defined as the limit of a function when delta tends to infinity. B of j to b of f. By the way, if we increase delta, this v changes, right? So this is the definition. And the theorem says that this power spectral density can be obtained from the autocorrelation function of this random process. Some textbook, I don't know whether you used which textbook, but some textbook defines the power spectral density using this formula. But that is not correct, okay? So I strongly recommend you to remember the definition and the theorem, because sometimes some property of power spectral density can be much better understood by simply using the definition of the power spectral density. For example, what happens if you delay a random process? Power spectral density changes? It doesn't, because the magnitude square is taken, right? Something like that. Anyway, and this looks very complicated, but the outer operation is Fourier transform with respect to the variable tau. And this capital A is time averaging with respect to variable t. And you have a two-parameter function, Rx, x, t plus tau and t. But initially, this two-variable function is defined as this one, if x is a complex valued random process. So this is the autocorrelation function evaluated at t1 and t2. For the theorem, we need to replace t1 with t plus tau and t2 with t. Got it? And this autocorrelation function becomes a single parameter function when it's stationary, or at least y-sense stationary, then there exists a single parameter function that satisfies this one. By the way, this one and that one, even though they share the same name, they are different functions. The function on the right-hand side is a two-variable function, and this is a single-variable function. And now, good thing is that Wiener-Khinchin theorem itself has a lemma or corollary like this. If the process is stationary, then we don't need time averaging, but Fourier transform of the autocorrelation function. And this is quite often used in estimating the power spectral density over random process. How? Well, we do not replace the Fourier transform, but we replace this again, statistical averaging, in estimating the autocorrelation function. By the way, in our textbook, it talks about auto-covariance estimation. And that is because sometimes we want to convert a non-stationary signal. Sometimes, not always, some non-stationary signal could be covariance stationary. In that case, for example, we have a 60 Hertz, some tone interference corrupted by some white band-limited white noise. In that case, if we remove the mean path or mean process, then we may have a stationary signal. So our textbook talks more about covariance estimation, but you may just say that, okay, autocorrelation estimation could be okay. So here comes how our autocorrelation function is approximated. So remember, exact Wiener-Khinchin theorem requires us to use statistical averaging, but we can't do that. So what do we do? Similar to what we've done in periodogram. Sometimes we just use a single realization and try to estimate the autocorrelation function. Sometimes we divide the entire observation interval into smaller segments, and then we hope to enjoy the averaging effect that reduces some effect of noise. And the details depends on your application, and I have no time to talk almost every part of it. Actually, I remember when I first came here at postdoc around 20 years ago, there was a graduate course teaching the spectrum estimation. I hope the course is still being given. So you may, as a if you have interested in radar signal processing or radio-based sensor system, if that course is offered, take it. And you will see a lot of periodograms, spectrograms, autocorrelation estimators, and those type of things. Anyway, so we replace the statistical average to approximate the autocorrelation function, and then we perform Fourier transform. That is also done for a discrete time random process. As far as we are concerned with a discrete time random process, and if we do time limiting, then we may rely on, again, DFT or its fast version, fast Fourier transform, to efficiently estimate the power spectral density. Okay, we are almost done. Just a second. I have written some, yeah, where is this? Yeah, something's missing. Just a second. Okay, here. So this small part is the kind of giving you a big picture. So we've seen the short-time Fourier transform and spectrogram to analyze a non-stationary signal. Actually, non-stationary random process can also be similarly analyzed. So this is for non-stationary signal. And this part is more for stationary signal or stationary random process. But I only talked about so-called non-parametric approaches. So in power spectral estimation, the first thing is you divide whether you are taking parametric approach or non-parametric approach. Here, parametric approach means that you have a finite number of parameters to approximate your power spectrum. So this part is covered in the next chapter. So let me go up. So this is parametric signal modeling is related to the parametric approach to power spectrum estimation. And you may say that, hey, what's the use of it? But actually, in voice compression or vocoders, this is a everyday practice. Still, it is used in many voice compression algorithms. And interestingly, our human vocal system can be well modeled by some parameter-based models with very few parameters. That is what those smart people in AT&T Bell Laboratories and the engineers at that age have discovered and has been used for a long time. However, currently, since we have a very high performance system, what happens? We just sample and send without compression. So it's amazing, right? We are kind of wasting our bandwidth even without compressing the acoustic signal. But anyway, so this part is for parametric approach. But in this chapter, especially at these two sections, we've done non-parametric approach. And in non-parametric spectrum estimation, the representative ones are periodogram and auto-covariance based approaches. Got it? So you've just seen these two. And these are on chapter 11. Okay? And we are almost up. Time's up today. And unfortunately, we have only one class meeting. And I have to talk a lot about AR, MA, ARIMA, and there are many models with only few parameters. So I'm not sure whether I can cover them all or not. And even if I talk about this part, I still want to talk about discrete Hilbert transform and Capstrom. Where this chapter, there is actually no chapter for this one, but it seems that I may not talk about the applications of DSP to AI, ML at all, unfortunately. Anyway, so this is the kind of big picture of the next class meeting. Okay, that's all for the day.